Thank you. So this talk will be about the Opus codec, which is some form of a follow-up on the Celt codec, which Tim Terryberry, another Opus developer, presented at LCA in 2009. So first, what is the Opus codec? It's an IETF standard currently under development, nearing the end, hopefully. It targets interactive audio transmission over the internet. Obviously, being at the IETF, we sort of had to focus on the internet. IETF being Internet Engineering Task Force. And interactive here means to have something that is suitable for two-way communication. Obviously, if you can do that, you can also do non-interactive applications, but not the other way around. So Opus aims to be royalty-free, just like Speaks, Vorbis, FLAC, and all the other zif.org codecs. So the code itself is BSD, and there are free licenses to the patents that apply to Opus. So the effort involves many organizations, including zif.org, Mozilla, Skype, Octasic, and Broadcom. And in terms of technology, Opus is actually a combination of the Silk and the Celt codecs. So just a brief history of where this all comes from. Opus originally comes from two independent efforts. One is the Silk codec that Skype started developing in 2007. The other one is the Celt codec, on which I started in 2007 as some sort of spin-off from the Ghost codec that I was working on with Monty Montgomery. So a first version was presented by Tim at LCA in 2009, at which point I was saying that we were planning on freezing the bitstream within the next few months. And then 2 months later, Skype came to the IETF and said, well, we would like to create a working group to standardize a free codec. And they obviously had Silk in mind there. To say that the proposal was controversial would be an understatement. There were big fights over that. As a sort of coincidence, a lot of the people who were opposed to creating such working group tended to work for companies that made huge amounts of money with patent licensing on standards codec. I don't know why. And so it took about a year with a lot of heated debate before the IETF agreed to create a working group to do this codec. They weren't allowed to say that it had to be royalty-free, but in practice, that's what we were doing anyway. Shortly after that, July 2010, we had the first prototype of a hybrid codec that combined Silk and Celt. Then the year after that, we were pretty close to freezing the bitstream, and we had some first listening tests where Opus was actually shown to be able to beat high-efficiency AAC and Vorbis, which were not designed for interactive, so that was quite a surprise for us. And as of November 2011, Opus is said to be in working group last call, and we've been doing the last very minor changes to the bitstream. So let's look at Opus in terms of its main characteristics. For sampling rate, Opus actually supports 8 to 48 kilohertz, which means anywhere from narrowband, which is what you have with a normal PSTN phone, up to full band, which is what you have on a CD that you buy. In terms of bit rates, it goes from 6 kilobits per second, so about 3 times as much as codec 2, but still quite low for everyone else. And it goes all the way up to 510 kilobits per second, which is fairly high and close to being the rate of the lossless codecs. It supports also variable frame size, which is relatively unusual for speech or audio codecs. So you can do very low latency with 2.5 millisecond frames, and it scales up to 20 millisecond frames, which are pretty much standard for voice over IP. It supports both mono and video, support for speech and music encoding, And what's actually special is that it's possible to change between all of these characteristics seamlessly in real time without having any glitches. So because of all of that, Opus is pretty much suitable for almost all audio applications. So here I've got this figure to show a bit where Opus stands compared to other codecs. What's pretty obvious is in terms of delay on this axis, Opus pretty much has lower or equal delay than any other audio codec out there. So it's pretty good for interactive applications. It also covers the entire range of bitrate. So unlike, for instance, Speaks, which has also reasonable delay, but only goes up to a certain quality because of its limit in bitrate. Vorbis scales a lot in bitrate, but has delay that is unsuitable to interactive applications. So Opus can pretty much replace all of these codecs for all kinds of applications. So these are just examples of applications where Opus is suitable. Voice over IP and video conference, obviously that is the main focus of that codec. It also works for music and video streaming or storage. There's even some people who have used this codec to do remote jamming. So two people playing an instrument at the same time over an internet connection and being able to synchronize each other. So that requires very low latency. It can work for wireless speakers, microphones. It works for audiobooks. There's some uses as well for virtualization and sound servers. Software like NetJack or Spice from Red Hat. So essentially it covers everything except two things. One is lossless, like what FLAC does, and the other end is ultra low bitrate, which is what Codec 2 covers. So these are the two codecs that Opus is not trying to replace. So this is the architecture of the Opus codec in terms of the two main components, which are Silk and Celt. So looking at the encoder, you have a Silk encoder that works in parallel with a Celt encoder. They all output to the same bit stream, and on the decoder end, you have the two parallel decoders. And there's three modes of operation. For speech for speech from narrowband to wideband, you actually only need the Silk part of Opus. So that's the only one that's working. On the other end, for music, you only want Celt. And there's actually a hybrid mode in between that is quite useful, where for very high quality speech, you can use both Silk and Celt at the same time to get fairly good quality. And the way that works is that Silk for speech is quite efficient at coding up to 8 kilohertz, and then Celt picks up and codes the remaining frequencies up to 20 kilohertz. So with that, you could actually have very high quality speech at 32 kilobits per second, full band. So quickly about the technology on the Silk part. I have not been involved too much in the Silk part of the codec, so I will just have a brief summary of what's involved in there. So Silk is fundamentally a speech codec. So it's based on linear prediction. I would say it's a bit like Speaks, but just much better for every single part of it. So it's very good at coding both narrowband and wideband speech, and it's mostly useful up to about 32 kilobits per second, at which point the quality for speech is very good, and it doesn't really help to have higher bit rate. It's not very good for music, which is the same for pretty much all of the specialized speech codecs. And it's also actually heavily modified compared to the original version that was submitted, so that it could fit well within the Opus codec. So it's not compatible with the original Silk codec that currently ships in the Skype client. On the Celt side, so Celt stands for Constrained Energy Lab Transform. It's designed to do both speech and music, and it can scale to very low delay. Like most general purpose audio codecs, it's based on the modified discrete cosine transform, or MDCT, just like Vorbis and in some way MP3 and AAC. It's most efficient on full band signals, and its useful range is around 40 kilobits per second and above. So in their original form, there was pretty much no overlap between Celt and Silk. And on the other side of Silk, so it's not, Celt is actually not very good for low bit rate speech. So here I have an overview of the entire Celt codec with high-level blocks. So as I said, it's based on the MDCT. It uses long blocks that can be up to 20 milliseconds in duration. And for things like transients, like drums or something like that, or just a new note, then it can actually divide the frames into tiny blocks of 2.5 milliseconds to code that better. So the whole key to the Celt technology is that it's trying to preserve the energy of each barred band at in any given frame. So no matter what happens or no matter what the bit rate is, Celt cannot create energy out of nothing in any frequency band, or it cannot make any band just disappear. And that is very different from codecs like MP3 or even AAC. And so Celt makes use of algebraic vector quantization for all the details within one band. I won't go into the details of that. And because of the low delay constraints, it's actually trying to minimize side information, because if you're sending 2.5 millisecond frames, you don't want much side information. So the block diagram here shows the signal going in. It goes through a pre-filter, which I'll talk about a bit later. Then it gets windowed and cut into frames, sent to the forward MDCT. From there, we actually measure the energy in each of the bands, and we code that explicitly. So in the bitstream, there is something, this is the energy in all of the bands. So that's how the energy is actually preserved. So energy is quantized on one hand, and then it's also used to normalize the MDCT coefficients in each band, and that gets quantized separately. On the decoder end, it's basically the energy multiplies the details that were encoded. We do the inverse transform. We stitch everything back together with weighted overlap add. And then there's a post filter, which I'll also discuss a bit later. So this was from the LCA 2009 presentation. We had a slide on future work, so let's see how that went. First point was freezing the bitstream format, and although that took a lot more than a few months, that is now done. And I'll go into the details of what we actually did to the bitstream. So first, we did many changes that were required for integration within Opus. Two of these changes. One is we had to change the layout of the bands such that we could actually have the same layout for all the frame sizes, which meant we could change frame size on the fly with no glitch or anything. Another change we did was we implemented 20 millisecond frames because Silk used that, so we tried to have some, we needed to have the same frame size. It also had the benefit of increasing the quality, because for music, if you have 20 millisecond frames, it's better than 10 milliseconds. Another thing we had was we did a lot of tuning to the static bit allocation. In Celt, the one way we reduce the amount of side information is that the bit allocation is frozen in the bitstream. So we had to tune that, because once the bitstream is frozen, you can't change it. And the main change we did was actually stop starving the high frequencies. That required a lot of listening tests to determine that this was actually the problem. So when looking at the bit allocation, in red you have the current bit allocation, which is final. And in blue, this is what we were using in, at the time of the last talk in 2009. So the main difference is that in all of this region in frequency, we actually have a lot more bits. So it makes it sound better. And it turned out that this region where we used to have more bits was not really useful, so we moved them around and just increased quality that way. Another feature we added was something called anti-collapse, which I'm discussing here. Turns out that the way we were chopping the frames into 2.5 millisecond small blocks, this was great to avoid pre-echo, but on the other hand, it could cause bands to collapse for short periods of time, like 2.5 milliseconds, and that could actually be audible, although not in this room, so I don't have a sample for it. But you can see on the spectrogram here, the x-axis is time, y-axis is frequency. So we see, for example, in this region, this is castanets, so we see that just before one click, we actually have everything collapsing to 0 because the energy is very low compared to the click, and we didn't want to introduce pre-echo. But that black region is actually audible if you have headphones. So what we did to come here with anti-collapse is we actually detected these holes and just filled them with noise. So it sounds a bit strange that we're adding noise as pre-echo, but in practice it turns out that it sounds better. Last main change to the bitstream that we did is per band time frequency modifications. So it means we could do the equivalent of long blocks and short blocks on a per band basis as opposed to per frame. So here I have an illustration of that. So one problem we have is basically we have to choose between having good frequency resolution or good time resolution. So in here, if we have some noise with this resolution, the noise gets spread in the time domain, but it's contained in the frequency domain, or we can do the other way. But fundamentally, the product of the time resolution and the frequency resolution cannot be lower than a constant. That is called Heisenberg's uncertainty principle, and as far as I know, we're just stuck with it. So this is what most codecs actually do, including Vorbis, MP3, or AAC. So this illustrates 3 different frames with a transient in the middle. So what will happen is normally we'll want good frequency resolution. When we have a transient, we say for this transient we want good time resolution, and then we go back to good frequency. And so what Cal can actually do now is that on a per band basis we can decide, well, in this band there's a transient, but we're mostly still hearing the tone from a previous frame. So we still want good frequency resolution there. On the other hand, for these bands, there's no tone, so we might as well have good time resolution. So that actually allows us to reduce the artifacts during transients. And this is an actual example of what the encoder currently does on this audio sample. So we can actually hear some guitar playing at the same time as hand claps. So, oops. Yep. So most of the spectrum is actually green, so we have good frequency resolution. And when we have hand claps, then we see this red. But the red does not necessarily extend all the way down, for example, here. So we can still properly encode the tones even during the hand claps. So that was for the bitstream. And then one other point that was in our future work was dynamic rate allocation, and that was also done. In terms of dynamic rate allocation, so as I said earlier, Celt mostly has static allocation, and that's the only thing we had back in 2009. And although that's been tuned, we can do a bit better. And now there's actually 2 ways to deviate from that static allocation. One is what we call the allocation tilt, which basically controls the balance between the bits we give to the high frequencies versus the low frequencies. So that gives us a bit of control over that. And there's also what we call a band boost, which means we can actually say that this particular band needs more bits. So we added something to the bitstream to just boost the allocation on a per band basis. We're still working on how to efficiently use that method, but at least we've frozen the bitstream in a way where we know that we can make a better encoder in the future. There's still some work in progress for using this band boost technique. So that was for dynamic allocation. We had improved stereo coupling, and that was done as well. For stereo coupling, now Opus, or the Kelt mode of Opus, has 3 modes now. One is dual stereo, so coding left and right separately. Not very interesting, but sometimes useful. We have mid-side stereo, which is really the interesting one. And there's intensity stereo, where we don't have too many bits, so we just downmix to mono and encode the energy difference between the channels. So for mid-side stereo, what we do is so it's mid-side means some indifference between the 2 channels. And we do that after having normalized by the energy, which means that no matter what happens, or if we mess things up in the mid-side, we still have not modified the energy, so we cannot add crosstalk or create really bad artifacts. So that makes the technique fairly safe. And again,
stereo, not binaural.
It can be used for both.
Okay, so there's still enough phase information there.
Oh yeah, we do. The question is there still phase information? And except for intensity stereo, we fully preserve the phase there. Okay. We're just talking here about reducing the bit rate by taking advantage of the redundancy between the channels. And so the way we do it, again, is we preserve the ratio of energy between the sum and the difference, which we encode as an angle here. That turns out to be optimal in terms of quality, and I won't go into the maths to prove that. And the only important thing to know is the bit allocation for mid and side actually depends on this ratio. And it also turned out that what we did for mid-side stereo turned out to be a very useful way to split some bands that were previously taking too many bits, because our code books have a limitation of 32 bits if we don't want to require 64-bit arithmetic. So if we have code books that are too big, we split the band in 2, pretend it's mid-side stereo, and then recursively do that, and we can actually encode up to code books up to 1024 bits with just this kind of split. So that was for stereo coupling, and last one was improving the pitch prediction, which was not very good. And on that one, help actually came from Raymond Chen, who works for Broadcom. And what he proposed was to replace our current pitch predictor by what he called a pre-filter post-filter that is mainly aimed at doing noise shaping. So the important part is, if you look at the frequency response of the post-filter here, this assumes that we have some a signal that is periodic. Whoops. So our signal will have a tone at this frequency, and so on. So what the post filter will do is, if we apply it on the decoded signal, then it will, assuming the noise before it is sort of flat, spectrally flat, it means that we're emphasizing the noise that is close to the tones we have, where it's not really perceivable, and we're reducing it in between the tones where it would normally be audible. So by doing that, then the total amount of noise we perceive goes down. And the idea of the pre-filter is only because the post-filter modifies the frequency response, so we need to have the opposite on the encoder side to make sure that the total frequency response of the system is still flat. So we did some subjective testing of the Opus codec. We compared it to several other codecs, including the AMR codec, Speaks, Vorbis, and some flavors of AAC. We did many tests during the development, and on the final version, what we have are 7 tests that were actually conducted by Google. We had 2 MOS tests that were done by Nokia, and we have 1 ABCHR test from some volunteers at Hydrogen Audio, which is an audio enthusiast website. So first, the Google test. There were 2 narrowband tests, one for English, one for Mandarin. And what these tests showed was that Opus was clearly better than both Speaks and ILBC for narrowband. It was also better than AMR AMR narrowband at 12 kilobits per second. We'll see that's not the case for lower bit rates. In wideband and full band, Opus was found to be much better than Speaks G722.1, also called Siren, and also G719, which is one of the recent ITU standards. It was also found to be better than AMR wideband at 20 kilobits per second. Again, not the same for low frequencies, for low bit rates. On a music test, Opus 64 actually had about the same quality as MP3 at 96. So we're actually much better than MP3 there. And the test was inconclusive when it came to AAC that was within the margin of error. And there were also some transcoding tests, and just found that there were no issue transcoding between Opus and AMR narrowband or wideband. So this here is the average of a clean and noisy tests that were done by Ansi Rameau from Nokia. What these tests showed was that compared to AMR narrowband here and AMR wideband, Opus, which is represented by these the yellow and the two red lines, depending on the mode. So Opus essentially does better than these ITU or 3GPP codecs at higher rates, and it does a bit worse at lower rates, which we didn't care too much about for voice over IP, so that's not a big loss. And at higher bit rate, it's actually fairly competitive with G718B, which is a very new ITU standard, and it's better than these two other ITU codecs, which are 722.1c, called Siren 14, and G729. G719. Yeah, it's much better than G729 there. And this last test was from done by some volunteers at Hydrogen Audio. It was a 64 kilobits per second test on stereo music, and it turned out that Opus was found to be significantly better than the high-efficiency AAC implementation from Apple, which itself was better than both the Nero implementation of high-efficiency AAC and Vorbis, and these two were actually statistically tied. So that was actually quite a surprise, because high-efficiency AAC has a latency in the order of 200 milliseconds, and we were operating at around 20 milliseconds latency. So I have a few samples here to give an idea of the kind of quality. So the first one is what you might be hearing when someone puts you on hold using a regular PSTN phone. So this is what you would be hearing. So this is what telephony people called uncompressed speech. Now, with exactly the same bit rate, which is 64 kilobits per second, with Opus you could actually do full band stereo, which means you would get this instead. And this here is the reference. I'm not sure you can actually hear the difference with the... No, I mean, I'm not sure you'll be able to hear the difference between Opus and the reference in this room, but this is the reference. There's a bit more noise, but the dynamic range should be the same. And this is actually what you get with MP3 at the same rate. So, yeah, MP3 sort of breaks down at those kinds of rates. So I also have a demo to show how Opus can actually change its bit rate on the fly. So in here, what I have is the same excerpts, but it changes bit rate continuously. It starts at 8 kilobits per second and it goes all the way up to 64. And that is illustrated in the bar here. So it starts at 8, and I'll play this. So this is really an extreme example. In a normal internet connection, the bandwidth tend to not go up by a factor of 8 in 15 seconds. But this just demonstrates that it's fairly easy to change the bit rate in real time and not have any sort of glitch or anything. So this is what we're currently working on. On the tool side, we're working on an OGG encoder and decoder. We've pretty much settled the exact format to use the OGG container with Opus. We're working on a Matroska encoder decoder. There's hopefully Firefox support coming along. We still need to decide on which container that would be. And so that's on the tool side. In terms of quality improvements, there's still a lot of quality improvements possible, because so far we've only focused on the quality aspects that related to the bitstream. Now that the bitstream is frozen, we can actually work on having a good encoder. So right now we're working on having better encoder decisions, so really tuning the encoder to increase the quality. Also working on the VBR side, because what we had even in the hydrogen audio test was VBR that was heavily constrained. It could not deviate too much from its average rate. And now we're working on a way to have the Opus encoder being allowed to use a lot more bits on audio contents that it knows is much harder for it to code. And the last one is automatic speech and music detection. So we could use the optimal mode. If we have speech, we may want to use Silk a lot more than if we have music. So it's much better if we can detect that automatically than asking the user. And here's what's the non-technical stuff coming up. On the IETF side, the next step is to go to IETF last call. Hopefully that should happen in the next few weeks. And after that, the next step is we have an actual Opus RFC. In terms of industry adoption, the main place where Opus we're really hoping will get adopted is for the upcoming RTC web standard, or WebRTC. The idea of that is to standardize video conference or voice over IP from within the browser. There's also browser support for HTML5 audio tags. That would be fairly nice. Also, well, that's not free software, but considering that Skype is involved, most likely the Skype client will probably be shipping that at some point. And in the future, I think everyone should be using Opus, except the ones using Codec 2 and FLAC. So here's our website. We've got a Git repository, IETF mailing list. There should be a more technical list created shortly. And we're always on #opus on the freenode.net. Any questions?
We have time for about 15 minutes of questions, if that's okay.
Oh.
Just on the world domination point, but I mean, we've had poor luck with getting anywhere with free codecs outside our little community. YouTube perhaps being one of the few examples where I can play something with a free codec. How do you see that changing? Do you see that your codec's so much better that you'll be able to get it picked up? I mean, how do you work through the world's MP3 players or those other things that could really benefit from these better and free codecs, yeah. But we seem to be stuck in the poor choice that we made 10 years ago from what we could pick up off the floor of MPEG.
So obviously there's no guarantee that everyone will be using it, but there's many things that are actually different this time. One is that we're actually in a standards organization, which is the IETF, and one thing that a lot of people used as a reason not to use Speaks or Vorbis was that, well, it's not really a standard, it's just this ziv.org weird people that are handling that. So that obviously changes. We actually do have support from many companies who actually want to deploy this. So we're not just trying to push it. There's many people who want to use it, including for this WebRTC thing. And in general, Opus does a bunch of things that no other codec can do. So we're probably not going to be pushing away, for instance, G729 in the applications where it's currently being used. However, for new applications, and there's a lot of them right now, and there's lots of applications where there's no other codec that works. So, or there's no other really strongly established standard. So this should be easier than trying to push
royalty bearing things into new spaces. You're hoping that someone will just pick up all this works and I'm not writing a check.
Yeah, I mean, obviously we're not going to replace MP3 overnight, but there's a large space of applications where we could just go in because there's no strong competition at this point.
Some bitrate questions. I wondered, when you played the bitrate sweep, it seemed like there was a very noticeable shelf at about between 30, 35 or so, where just all of a sudden all of the high tones were no longer as muted. Was that it switching modes or something else? Yes,
what happens basically is that what you were hearing at 8 kilobits per second, only because of the bitrate, Opus was actually coding the audio only up to 4 kilobits, up to 4 kilohertz, and it was down mixing to mono. Otherwise, the artifacts would be there would be just too much artifacts. And as the bitrate went up, then the bandwidth got wider. Around 30 something, it went to full band. Around 40, it switches from mono to stereo. So in some of the places, the difference is quite large, so that's what you hear. In a normal application, that would not happen very frequently to hit these transitions.
And do you have a constant bitrate mode or some simulation of one to handle the case of encrypted audio safely?
This, in some sense, is two different questions. So first, yes, we do have a pure constant bitrate. We have a constrained variable bitrate, and we have fully variable. The second comment I'd like to make is that the whole thing about encryption and VBR is, in the vast majority of applications, really blown out of proportion. But we still support CBR.
So I guess, I mean, am I looking at encoding my entire CD collection again in Opus? How does it perform at the kind of bit rates that I've been using for OGG currently? Have you testing stuff for that?
Yeah, so we haven't done much testing at higher bit rates. One of the only real comparison we did was 64 kilobits per second. I expect the difference to be smaller for higher bit rates. It's actually very hard to test. We're about to start a test with the Hydrogen Audio folks at 96 kilobits per second. And above that, the differences become so subtle that it's really hard to get statistically significant results. In the end, especially for these kinds of high rates, you're not likely to see a huge difference between Opus and Vorbis either way. So if you're going to be re-encoding your music collection with Opus, it would not be for quality reasons. Maybe at some point, if browsers get Opus support, then that could be worth it. But there's no really big difference with Vorbis, unless you go to lower bit rates and speech and things like that, where Opus is much better.
So, a quick one: how would you characterize the CPU complexity for encode and decode? In terms of MP3, Vorbis, AAC level?
So for decoding, I would say that Opus is probably slightly more complex than Vorbis. On the encode side, there's actually a huge variability. There's a complexity knob that can be tuned to say I want higher quality at the price of more CPU or lower. Actually, for music where you're only using the Celt mode, which is less complex than the Silk mode, the complete Opus encoder will likely be much less complex than the Vorbis encoder. And there's actually a fixed point, there's a fixed point encoder and decoder for Opus. So it can actually run in real time on vast majority of the embedded devices now.
I'm not sure whether you see potential, but in cases where it might be possible to do multiple passes of an audio stream could you see improvements that you could do with the variable bitrate encoding if you can do multiple passes?
Right now, not that much. There may be some code that could be added for that, but the work we're currently doing in terms of VBR is to actually say, this is the quality that I want, and use whatever bitrate you think you need for this file. So we can end up with, if we use really fully unconstrained VBR right now, which is only experimental, and we ask for 64 kilobits per second, many files will end up like at 60 kilobits per second, and once in a while you'll have one file that goes to 100 or something like that, because it was just much harder to code. So over a music collection, it'll average to 64, but there can be large variability. Obviously, if you're doing anything real time, then you want the constrained VBR that does not do that.
I noticed that in the API,
okay, sorry.
you only could use 1 or 2 channels, and also bit rates were quite, only had a very limited selection. Is that something inherent in the codec, or that will change in future?
Sorry, is what inherent to the codec? I missed the first part.
You've got the sample rates as like about a set of 4 or 5 different ones, and there's only 1 or 2 channels. For something like video streaming of like an actual movie, say from Netflix, Hulu, whatever, you might want actually multi-channel audio. Is that something that you can do with the codec?
Yeah, okay, so there's two independent issues there. In terms of sampling rates, the sampling rate that the current API will take are 8, 12, 16, 24, and 48. For different sampling rates, you just use...
There's no 44.1 for CD quality?
For that, you actually want to use resampling. And for example, the OGG encoder we have right now will just transparently resample to 48. And if you decode, it'll resample back, and that's really not an issue. It makes things a lot simpler, and that's part of what allows us this great flexibility in frame size and all of that. In terms of number of channels, the low-level encoder only does mono and stereo. However, for example, in the OGG mapping, and that can be done in Matroska and everything else, we can support multi-channel simply by encoding multiple mono or stereo streams. For example, you would probably want to couple the left and the right and also couple the rear left, the rear right, and then maybe have the center being independent. And we defined how to put that all together in a single packet. So that's how you would do multi-channel with Opus.
My question's to do with the speech codec. Have you stopped work on that now? Are we going to see a sort of a 1.2 stable release? And is it just going to drop off and Opus will take over?
Yeah, so I'd like to really apologize for the lack of maintenance on the speak side. What is currently called 1.2 RC1 would normally have been 1.2 if not for the other DSP stuff like the noise reduction and all of that wasn't quite ready for prime time. So I meant to actually split that together and call the codec part 1.2. Don't actually expect much change on that side. Even the DSP stuff is not nearly as good as what Google released in its WebRTC code base. So there probably needs to be a bit more maintenance, and if anyone knows of a maintainer who would be interested, that's possibly something that could be arranged also to get better support. Sorry about that.
I'm curious, where does the modern audio codec developer get a psychoacoustic model these days?
I don't know. Opus has no psychoacoustic model. or at least none that looks even remotely what is in MP3, and I don't know what AAC does. We ended up figuring out that a lot of the really fancy psychoacoustic curves and all of that is actually not that useful once you do the basics, which is constraining the energy in each band and having a decent rate allocation. A lot of the fancy stuff was just not useful, at least not for Kelt.
Are there any other questions? No. In which case, please allow us to thank you with this gift from Linux Australia. Thank you very much.
Thank you. That Skype started developing in 2007. The other one is the Kelt codec, on which I started in 2007 as some sort of spin-off from the Ghost codec that I was working on with Monty Montgomery. So a first version was presented by Tim at LCA in 2009, at which point I was saying that we were planning on freezing the bitstream within the next few months. And then 2 months later, Skype came to the ITF and said, well, we would like to create a working group to standardize a free codec. And they obviously had Silk in mind there. To say that the proposal was controversial would be an understatement. There were big fights over that. As a sort of coincidence, a lot of the people who were opposed to creating such working group tended to work for companies that made huge amounts of money with patent licensing on standards codec. I don't know why. And so it took about a year with a lot of heated debate before the ITF agreed to create a working group to do this codec. They weren't allowed to say that it had to be royalty free, but in practice that's what we were doing anyway. Shortly after that, July 2010, we had the first prototype of a hybrid codec that combined Silk and Kelt. Then the year after that, we were pretty close to freezing the bitstream, and we had some first listening tests where Opus was actually shown to be able to beat high-efficiency AAC and Vorbis, which were not designed for interactive, so that was quite a surprise for us. And as of November 2011, Opus is said to be in working group last call, and we've been doing the last very minor changes to the bitstream. So let's look at Opus in terms of its main characteristics. For sampling rate, Opus actually supports 8 to 48 kilohertz, which means anywhere from narrowband, which is what you have with a normal PSTN phone, up to full band, which is what you have on a CD that you buy. In terms of bit rates, it goes from 6 kilobits per second, so about 3 times as much as codec 2, but still quite low for everyone else. And it goes all the way up to 510 kilobits per second, which is fairly high and close to being the rate of the lossless codecs. It supports also variable frame size, which is relatively unusual for speech or audio codecs. So you can do very low latency with 2.5 millisecond frames, and it scales up to 20 millisecond frames, which are pretty much standard for voice over IP. It supports both mono and video, so synchronize each other, so that requires very low latency. It can work for wireless speakers, microphones, works for audiobooks. There's some uses as well for virtualization and sound servers, software like NetJack or Spice from Red Hat. So essentially it covers everything except 2 things. One is lossless, like what FLAC does, and the other end is ultra low bit rate, which is what codec 2 covers. So these are the 2 codecs that Opus is not trying to replace. So this is the architecture of the Opus codec in terms of the 2 main components, which are Silk and Kelt. So looking at the encoder, you have a Silk encoder that works in parallel with a Celt encoder. They all output to the same bit stream, and on the decoder end, you have the two parallel decoders. And there's 3 modes of operation. For speech speech from narrowband to wideband, you actually only need the Silk part of Opus, so that's the only one that's working. On the other end, for music, you only want Celt, and there's actually a hybrid mode in between that is quite useful, where for very high quality speech, you can use both Silk and Celt at the same time to get fairly good quality. And the way that works is that Silk for speech is quite efficient at coding. Thank you. So this talk will be about the Opus codec, which is some form of a follow-up on the Celt codec, which Tim Terryberry, another Opus developer, presented at LCA in 2009. So first, what is the Opus codec? It's an IETF standard currently under development, nearing the end, hopefully. It targets interactive audio transmission over the internet. Obviously, being at the IETF, we sort of had to focus on the internet. IETF being Internet Engineering Task Force. And interactive here means to something that is suitable for two-way communication. Obviously, if you can do that, you can also do non-interactive applications, but not the other way around. So Opus aims to be royalty-free, just like Speaks, Vorbis, FLAC, and all the other ZIF.org codecs. So the code itself is BSD, and there are free licenses to the patents that apply to Opus. So the effort involves many organizations, including ZIF.org, Mozilla, Skype, Octasic, and Broadcom. And in terms of technology, Opus is actually a combination of the Silk and the Celt codecs. So just a brief history of where this all comes from. Opus originally comes from 2 independent efforts. One is the Silk codec, support for speech and music encoding. And what's actually special is that it's possible to change between all of these characteristics seamlessly in real time without having any glitches. So because of all of that, Opus is pretty much suitable for almost all audio applications. So here I've got this figure to show a bit where Opus stands compared to other codecs. What's pretty obvious is in terms of delay on this axis, Opus pretty much has lower or equal delay than any other audio codec out there. So it's pretty good for interactive applications. It also covers the entire range of bitrate. So unlike, for instance, Speaks, which has also reasonable delay, but only goes up to a certain quality because of its limit in bitrate. Vorbis scales a lot in bitrate, but has delay that is unsuitable to interactive applications. So Opus can pretty much replace all of these codecs for all kinds of applications. So these are just examples of applications where Opus is suitable. Voice over IP and video conference, obviously that is the main focus of that codec. It also works for music and video streaming or storage. There's even some people who have used this codec to do remote jamming. So 2 people playing an instrument at the same time over an internet connection and being able to